And as I said, we will now continue with spectrometry of electrons and positrons. That means light charged particles. And first part will be about interactions, yeah, of these particles. Okay. And how it looks like this interaction, yeah, that that there are two main possible interactions. It is ionization, yeah, which is main interaction of this charged particle with matter. That means that these particles will lose energy as they ionize and excite atoms. Second possibility for charged particles, but this is mainly for this heavy particle. It is scattering by Coulomb field of nucleus or by field of electrons. For heavy particle, it's difficult to change direction, to be scattered on electrons because they are heavy. But for light particles, it is possible also by collision with electrons to obtain big change of direction. This is also a very special type of interactions for light particles, because for any charged particle which is moving with some acceleration, yeah, this is some irradiation of electromagnetic waves or electromagnetic radiation. And okay, if you have a particle which have very high energy or that has velocity, high velocity, in this case, this energy which is transferred to electromagnetic radiation, it's high. That means in this case, these emitted photons will be in the range of gamma radiation, and with energy or wavelengths which is near to gamma radiation. And this is named as Bremsstrahlung radiation. That means if this light charged particle is moving through matter, and by interaction with nuclei will be produced some accelerated motion, it will be emission of electromagnetic radiation, and in the case of gamma radiation. This is for very high ultra-relativistic energies. It is also possible not only emission of gamma photon, but it is also possible to produce pair of electron and positron. This is something as creation of pair production by photon. Yeah. Okay, this is third possible interaction of charged particle. And fourth, it's Cherenkov radiation. Cherenkov radiation is radiation which is emitted by charged particle which is moving faster than light at given materials. Yeah? And in this case, this energy or wavelength of this radiation is again electromagnetic radiation, but this wavelength is in the range of visible light. That means much longer wavelength and smaller energy of photon. Yeah, that influence of losing energy by Cherenkov radiation, it's negligible. Yeah, that means it is not for detection of energy or for stopping of this particle. But this is possible to detect this Cherenkov radiation, and from this to obtain some information about this this charged particle. Okay, this scattering, as I said, is induced by interaction with atomic nuclei. Yeah, and in this case, it's this dependency of such interaction. It is on the square of atomic number. Yeah, that this is from Coulomb interaction. And second possibility is scattering on or interaction with electrons in atomic cloud, but in this case, this function, this dependency of probability of such phenomena is given by atomic number. That means by number of electrons which are in the atom. Yeah. For heavy particles, we have mainly interaction with nuclei, yeah, because in the case of interaction with electron, this loss of energy is very small. Yeah. For very high energies, and we will discuss this situation later. And it's also possible, if you remember, we already discussed this high energy gamma, and it is very similar. Because if you have electron in the start point with very high energy, dominant process will be this Bremsstrahlung radiation. And what is Bremsstrahlung radiation? This is production of gamma with very high energy. Yeah? And if you have gamma with very high energy, you remember that this probability dominant phenomena of interaction is pair production. That means production of electron and positron. And if this gamma has very high energy, also this electrons and positrons have very high energy. Yeah? And that means this is very big probability for Bremsstrahlung radiation. And again, you will obtain new gamma. That means on the end, you will obtain many of gammas, electrons, and positrons. That means all what it's named as electromagnetic shower. Yeah, you will obtain electromagnetic shower, which is the same electromagnetic shower which you will obtain for gamma with very high energy. What is important for this charged particle? It is movement in magnetic and electric fields because it is possible to use this movement for determination of momenta or energy. Yeah, and we have in this case magnetic or electric spectrometers. Yeah. First process, which is the most important, because as I said to you, mostly our detectors are built on this, that they detect this ionizing particles. Yeah. And charged particles which are moving through this material, and that make ionization, and they have ionization losses. If you have neutral particle, it is necessary to convert this energy of neutral particle to this charged particle. Yeah. In the case of electrons and positrons, which are light particles, mostly they are relativistic. This is also one very important difference between heavy particle and light particles, between electrons and positrons and protons. It is that during interaction of protons only with electron, because proton is much, much heavier than electron, only a small part of this proton is transferred to electron. But for interaction of electron or positron with electron, the masses of these two particles are same. Yeah, that means this transfer of energy, it is possible to be also very big. It's possible to lose very big part of their energy for electrons during ionization. And a very special case is electron. Because electron, if you have interaction of electron with electron in atomic cloud, on the end you have two electrons, and they are quantum objects. That means that it is not possible to distinguish between these two electrons. It is not possible for you to know which electron is which is this primary and which is this secondary, which was in this atom. But it is not possible to obtain this information for you, but it is also not possible to obtain this information for God. That means that also physics is not possible to distinguish this. That means it is also influence of this phenomena to this description of ionization losses. And we expect that this particle, which is this primary particle, will be this which will have a higher energy. That means that in this case, it is possible to lose for electron half of energy maximum for during this ionization. And okay, this is a very important thing because, as I said, it has influence also on this description of this ionization losses. Okay, interaction of positrons are also special. In this case, it's possible to distinguish between positron and electrons. They are different particles, yeah? They have the same masses, but they are different. But on the end of positron path, it will be annihilation. Yeah? It is some probability of annihilation also on the flight. Yeah, that means during this movement. But this probability is very small. But most of positrons annihilate only on the path end. In this case, it will be in the rest, this annihilation. You will obtain energy which is given by two rest masses of electron and rest energies, and this is approximately 1.22 thousandths of MeV, and also this energy will be in the form of two gammas. It is necessary to be two gammas because we already had this annihilation in the rest. That means momenta was zero. Yeah. And on the end, you need to have also momenta of zero. And if you have only one gamma, it is not possible to be. Yeah. That means it's necessary to have two gammas, and these gammas should have the same energy and same momentum. Yeah? That on the end you have energy of this gammas 511 keV. Yeah. This ionization is described by ionization losses, and this ionization losses, this describes this energy losses by this ionization. And this is minus change of energy per unit of length. Yeah, should be minus because this change is decreasing. That will be minus, and minus times minus is plus. That means, okay, you have this energy losses. Okay, it's possible to derive equation for ionization losses, and there are, I will show you classical derivation. But this classical derivation, it is necessary to say that it is for non-relativistic and also for a heavy particle. I will say you why for a heavy particle. That means it is not for electrons and positrons. Okay, this is possible also not classical derivation, but quantum derivation for non-relativistic particle. But after that, it is necessary to do relativistic corrections and corrections on this identity of these particles for these electrons, and also this special corrections which is given by this. But we will mostly I will show you this derivation and we will discuss something about this relativistic correction, but only a few remarks and statements. This formula, which you will obtain for this ionization losses, it is named as a Bethe-Bloch formula. Yeah? And it is, as I said, classical derivation. And in the case of non-relativistic velocities, that means velocities which are smaller, much smaller than velocity of the light. And okay, this and also for heavy particle, that during one ionization, this loss of energy will be very small, negligible. Yeah. For one ionization, this change of energy will be negligible. And also this path of direction of movement of particle will be negligible changes. Okay, we want to calculate change of momenta by this interaction. Yeah? And this is possible to calculate using force which is act on this particle during whole time in which this particle is moving around this electron. Or we will look on it from point of view of this electron, and okay, that will be moving of electrons around this heavy particle. Okay, these forces are clearly these electric forces, and it's possible to calculate by Coulomb formula. Yeah, here this is okay. This is distance of this particle. Okay, and we use here parameter which is named as impact parameter. Yeah. Okay, here is a Czech description, but okay, this is description of this force. Yeah, this electric force, and this is in the case of ions. It is because you have electron and ion, it is attractive force. But okay, here is a movement of this electron around this ion, which is moved in this material. Yeah, and the smallest distance to this, if there will be no interaction, it is named as impact parameter. Yeah, that this is impact parameter. And this impact parameter will change only slightly. This distance will change during this interaction only slightly. This is given by this, that this is very heavy, and this change of trajectory of this heavy ion is very, very small. Okay, in this case, that means if you will look on it, if you have this contribution to this force, yeah, this projection of this force in longitudinal direction, they are same and opposite if this particle is in this direction. Yeah? That means here you have any acting of this longitudinal force. It is after change, after going near to this proton, for this electron, it will start to be in opposite direction, but this with the same magnitude. And on the end, this longitudinal change, influence of these longitudinal forces will be zero. The sum of this influence. It will be only influence which will be in perpendicular direction. Yeah. Okay, that this is this here, this force which is possible to calculate. This is this. Yeah, and if you know that this Coulomb interaction, it is in the direction which is from one particle to second particle. And as I said, influence has only this perpendicular force. Yeah, this is Houlle force, and here you will calculate this direction only to this perpendicular. That means it is only calculation geometry, pure geometry, and you will calculate from this force, which is possible to calculate here, and you will calculate only this perpendicular direction. Okay, fine. We will go from path to velocity. Yeah, that means this path which is run. It is given by velocity and by time which was necessary. Yeah. Okay. That this change of velocity, we will expect, as I said, that this change of energy, change of momenta, change of velocity is negligible against the whole velocity. That means this transferred momentum, it's possible to calculate by this force. And here from this dt, we go to dx. Yeah, that we obtain this dt is dx divided by v. Yeah, that means we will obtain this. Okay, it is this perpendicular part of this force is possible to calculate, and we will put here again this f. This force is here, and here is from minus infinity to plus infinity. Yeah? That's in all direction. Yeah? Okay, we will put here, and it is only this x. This is independent on path. Yeah, that means it is constant. Yeah, and you will make integration. Okay, it's possible to derive. But also it's possible to look to some tables of integrals, and or it's possible to use some program for calculation of integrals, and you will obtain this. And okay, we will go from minus infinity to plus infinity. If it is infinity, it's possible this b it's possible to neglect. Yeah. Then in any case, it will be minus infinity or plus infinity, it will be infinity, yeah, because it is square of infinity is infinity, and from this it will be also x. And here you have one time plus infinity, minus infinity, that means plus infinity, that means it is infinity divided by infinity, this is 1, or x divided by x, it is 1, and 1 times it is minus, is plus, second is minus, this is plus, that means 2 times. That means exactly from this you will obtain only this plus 2. Yeah? Here is b square, here is b. This is 1 divided by b, this is this, and you will obtain this. Okay, this is change of momenta. This is momenta which were obtained for electron from this ion during ionization. Okay, we know this momenta which obtained because electron was in the rest at the start, and after that it obtains some energy and it has some momenta, and from this momenta it's possible to calculate kinetic energy. We expect that again we have a non-relativistic approximation. That means it's possible to use this non-relativistic formula. Okay, that means this is momenta squared divided by 2 times rest mass. Fine. Okay, we will put this here, and we will obtain kinetic energy of electron, which was given by one ionization, one interaction with given impact parameter. Okay, fine. We will look here. That means if this proton or some another particle, heavy particle, is moving through matter, it is possible for them to meet many electrons. Yeah, and we are now looking on electrons in which distance this impact parameter from this ion in electron will be b. Yeah, okay, that means it will be in this ring. Yeah, we have very thin cylinder, cross section b from b plus small db. Okay, fine. And how many electrons will be in this cylinder? It will be density of electrons times 2 pi b, this is this ring, times dB, and times this dx, this is this path in which this heavy ion was moved. Yeah? That means we will have this cylinder and we will calculate how many electrons this ion will meet. Yeah? Okay. Total energy losses at this cylinder, yeah, it will be kinetic energy, which we already calculated for this given B, for this given impact parameter, yeah, times number of this electron, yeah, and we will multiply by this. Number of electrons at the cylinder, okay, and now we want to calculate all energy losses in whole roll. That means not only for one impact parameter, but for impact parameter from 0 to infinite. Yeah, okay, fine. We will make integral of this kinetic energy times this dn. Yeah, and okay, we will put here, this is 2 pi times b times db. Here is this dx. Okay, and we know this kinetic energy. It is here, yeah, and we will put here. Okay, we put here in this integral only this part, which depends on this impact parameter. Yeah, okay, that this is this, and here we have constants which are not independent on impact parameter, and here we have number of electrons. And what is number of electrons? Number of electrons is given by number of atoms times atomic number. That's number of electrons is given by atomic number, and okay, that's number of electrons is possible to calculate using atom density of material and atomic number. No, and atom density is possible to obtain from material density, Avogadro constant, and atomic mass. Yeah, that's known formula. Yeah, and it is possible to use, and it is possible to put this number of electrons here, and you will obtain this. That means this energy losses per dx, per this, yeah, per length unit, this ionization losses, we will obtain this, and after putting this number of electrons here. Okay, now what means this integral? This integral is a little problematic, yeah, because if you will look on it, it is a divergent integral if it is going from 0 to infinity. But it is necessary to say that these limits of integration are not in reality from 0 to infinite, but they are from some minimal value to some maximal value. And what are this minimal and maximal value? This minimal value of impact parameter is given by maximal energy, which is transferred during head collisions. That means this electron, if you will look on it from point of view of electron, it is moving and it is collision with this proton or another heavy ion, and it will go in opposite direction. This will be this head-head collision, yeah, backward scattering, yeah, and it is moving in opposite direction. If this mass of this heavy ion is infinitely large against this mass of electron, that means for proton it is 2000 times heavier, this, yeah, but it's possible to say that we will have some limited case. It will be head-head collision on the non-moving heavy object. In this case, this change of momenta, yeah, in this case, this maximal change of momenta will be 2 times, yeah, momenta of this electron. That means, and this momenta is given by velocity of this electron. That means this maximal change of momenta is this, and this change of momenta, yeah, it's from this it's possible to calculate maximal transferred energy. Yeah. Okay. Again, we are using this p square divided by 2 times mass. That means this will be 4 m square v square by dividing 2. This will be, okay, this will be 2. 4 divided by 2 is 2. And this mass divided by mass, mass square divided by mass is mass. V square will be here, and you will obtain this. Yeah? Or you will use this, that it is 1/2 on mass times 2 times V square. Yeah, that, okay, you will obtain this energy. That means maximal energy is this. And because you have relation between energy kinetic and momenta, yeah, it's possible to calculate which will be this minimal impact parameter for this maximal energy. Okay, that means it's possible to calculate this, and that means this is this energy which is here, yeah, and you will calculate from this minimal value of impact parameter. Yeah? Okay, that means we have this minimal value of impact parameter. Minimal transferred momenta depends on energy which is necessary for ionization. Because if energy will be smaller, which if this transferred momenta will be smaller, it will be not possible to be ionization. That means if we know mean ionization potential of electrons, in this case, which we named as I, it's possible to calculate this momenta using velocity and this ionization potential. Okay, again, if we know this minimal transferred momenta, it's possible to obtain minimal energy, which is connected to this, and on the end we will obtain this minimal energy which is produced. And again, if we know this minimal energy, we will obtain maximal momentum. Again, energy, kinetic energy is this, which will be transferred to electron. Here is derivation of this by impact parameter, and okay, it's possible to calculate this impact parameter, and you will obtain this. Okay, fine. In this case, we will determine this integral. Yeah, this integral of 1 divided by b. It is logarithmus, and this logarithmus is from b max to b min, and this ratio between b max and b min will be here. Okay, this is the maximal value of impact parameter here, and here is this minimal value of impact parameter, and here you see that this is same value, same value, same value, same value, and on the end you will obtain that this ratio of this maximal and minimal impact parameter is here. Okay, you will put this here, yeah, logarithms of this, and you will obtain this equation. And this equation is named as Bethe-Bloch equation for description of ionization losses. It's possible to calculate this ionization losses. And what means this equation and different parts of this equation? This first, it is connected only with constant, which is necessary for different unit system which you use. That means we use SI unit system, and okay, that means it is in this case it's necessary to have this. It is very oftenly it is also possible to put this constant to 1, to work in some special system of units. Okay, fine. Second part is named as main dependency on particle velocity, yeah, and also on material and also on charge of this particle. That this is the main dependency on particle feature, yeah. And it is given a square of square of charge of this particle, and square is from this reason because this is Coulomb interaction. Yeah, and this is dependency, inverse dependency on square of velocity. Yeah, they are very important because they will say you that with increasing velocity, very quickly ionization losses are decreasing. And on opposite, if you will start to decrease velocity, this ionization losses will very quickly increase. Yeah? And this is also very big dependency on charge of particle. It is square dependency. That means for a heavy particle which have high charge, heavy ion, you will have very high, very large ionization losses. Third part of this equation is main dependency on material properties. This is dependency on features of material, and it is given by proton number, that means atomic number of this material, and it is only linear, and it is clearly given only by this how many electrons you have in atom. This is exactly only this multiplying here. Yeah. This is this dependency on material and on atomic number of material, and also it is dependency on density of this material and in principle also on mass number, because it is influence of this atomic density here. And last part is a weak dependency on particle velocity and material properties. Here you have dependency on square logarithms of square of velocity, and here this is also dependency on ionization potential, which is necessary for ionization of this material. Okay, but the most important, what is necessary to remember, that for ionization losses, for ionization, we have square dependency on charge of this particle, linear dependency on atomic number of this material, and inverse dependency on square of velocity of movement of this particle in material. Okay. How will be if we need to put relativistic corrections? Yeah, it was non-relativistic case. That means heavy non-relativistic particle. Yeah, for relativistic correction, again, it is necessary to correct this maximal transfer momentum by this coefficients which is given by this relativity. And also we have some reduction of particle electric field in the direction of light by this, again, by relativistic factor. And in the perpendicular direction, it is increasing by this factor. On the end, we will obtain this corrections. Here it is no corrections. Here is beta square, but it is only that we have this velocity in the units of velocity of the light. Yeah, that means beta times c, it is this v. Yeah, it is this velocity. And it is possible to do in this case that here now we have this electron rest energy, and here we have velocity in the velocity of the light. And if this velocity is very near to velocity of the light, it will be near to 1. Yeah. Okay, but here you have some changes, and okay, it's possible to put together these two logarithms. Yeah. Okay, you will obtain this, and okay, you have this part, this fourth part is changing. If you will look on it for a case in which this velocity will be much smaller than velocity of the light, how will be? In this case, beta square is 1. Yeah? Okay, no. If velocity is very small, again c, beta square is 0. Yeah, beta is 0 because v divided by c, it's very small. It is 0. And how it is here? If beta square is very small, yeah, against 1, it's possible to neglect. Here will be only 1. Here we have c square times beta square. This will be v square. That's fine. This is the same. You have 2 times rest mass of electron times v square divided by ionization potential. It is exactly what we have here for non-relativistic case. Okay, from this logarithms, and okay, it's fine. And we have the same equation as we obtained for non-relativistic case here. Yeah? That means this relativistic equation is going to this non-relativistic approximation. Okay, the same formula, this Bethe-Bloch formula, is for electrons is even more complex. Yeah, as I said, in this case, it is also working this situation that this electron has the same mass as electron in atomic clock, and this maximal transferred energy is E divided by 2, and on the end you will obtain very complex function and very complex equation. Yeah, for complicated. It is not necessary to remember. Yeah, that's it. In the case of necessity, it's possible to check from literature or from tables. How it looks like for lower energies. In this case, these light particle losses are thousands times lower than for heavy particles or heavy ion. Yeah. If energies are high and this heavy particle starts to be relativistic also, that means these energies will be near to GeV, these ionization losses of light and heavy particles will be comparable. This light particle will be slightly lower. How it looks like if you will check dependency of this ionization losses on velocity or momenta of this particle. Here it is for different particles, and here is multiplying on beta gamma. This is this relativistic part. That this is ratio between V and C, and gamma, if you remember, this is this relativistic correction, 1 divided square root from 1 minus beta square. Yeah? And what we see? We see that it is very quick decreasing of ionization losses with increasing of energy. This is this V square. Yeah? But for some value, because velocity starts to be near to 1, we will obtain minimum. Yeah? After that, starts to have a big influence, this logarithms of V square. Here, increasing velocity will have influence that will increase this ionization losses. It will be go against this. And on the end, you will obtain change of decreasing to increasing. Yeah. And what is important, we have some range of velocities for which it is minimal ionization. And these particles are named as minimal ionizing particles. And for example, if we have particles which are produced in atmosphere by cosmic rays, you will have a shower of minimum ionizing particles, mostly muons, and these particles is possible to use for calibration of detectors, for example, because they have the same ionization, and we know which will be value of this ionization for different materials. Here is, for example, for hydrogen, helium, and up to lead. Yeah, and okay, that means it's if you have some thickness of this scintillation detector, for example, you know how will be losses for this minimum ionizing particles which are running through this thickness. And, okay, it's possible to use for calibration of such detector. Okay. I said to you that for light particle and also for heavy particle, and mostly for heavy particle, it is also possible to be elastic scattering. Not only on electrons, but also on heavy atomic number. These heavy particles, for them it is important only scattering on atomic nuclei. I said you during this description that here influence of scattering of some heavy particle on electron will be negligible. Yeah? That means it is small. For light particles, it is in different situation. Here is important also scattering on electrons. Yeah? Okay, it is possible to have single scattering. It is in the case that this thickness is very, very small against this cross section. There are few scatterings if it is approximately same, and if you have this thickness in which this particle is running high, and you will against this absorption length or interaction length, in this case this you have multiple scattering. This single scattering in the electric field, it's possible to describe by Rutherford scattering. Yeah? Okay, it is not necessary to neglect to remember here. I don't know if you already has lecture with derivation of this Rutherford scattering, but okay, this is not important. But it's from this Rutherford scattering, it's possible to derive relation between angle of this scattering and this impact parameter. Again, remember that this impact parameter, this is the smallest distance in which will be this particle if will be no interaction. Only moving around. For heavy particles, the scattering angles are very small. In this case, this path is only slightly undulated. It's very small changes of this path. For light particles, for these electrons, because if you have scattering on electrons, it will be scattering to large angles. Yeah? That means in this case, this path is, and the range of this particle is not defined. We have losses of particles during whole movements through this material. It is necessary to calculate not the mean value of this scattering angle, but it's necessary to calculate square of this. Yeah, because this scattering is possible to be to any direction. Yeah. Not only in one, and mean value in this case will be, because this is the same probability of minus scattering to plus scattering. That means on the end you will have the mean value will be 0 if you you have movement in the x-axis. Yeah. If we have this heavy particle and small scattering angles, yeah, we will obtain. It will be maybe during exercises we will discuss, but now it's so difficult for you, I think, that we will know derive. But what is important in this case? In this case, it's important that you have, in this case, dependency, square dependency of this mean value of square of this scattering. That means you will have this direction of this beam of particle will be still same. Yeah, this centroid will be in the same direction. What will be dispersion? Yeah, it means it will be this radius of this beam will increase by this scattering, and this increasing is given by square of this charge of this particle, of this ion, square of this Z number of this material. That means this nuclei, again, here is square and here is square. This is from this reason, because in this case, this is this Coulomb interaction. And it is inversely dependent on the square of velocity, yeah, because momenta is mass times velocity. That means here is velocity square and here is also velocity square. And this is very important because you see that if velocity will be very high near to velocity of the light, it will be small dispersion of this beam. Yeah? If velocity will be small, it will be very big spread. And if you will have a heavy ion, it will be, and heavy material will be higher spread of this higher dispersion and higher radius of this beam. Yeah. Okay. For light particle, I said to you that second very important process is this Bremsstrahlung radiation. Yeah. This accelerated charged particles emits electromagnetic radiation, and for high energy particles we have high energy gamma radiation. Yeah. This energy, this losses of energy this Bremsstrahlung energy, energy of Bremsstrahlung radiation is linearly, or not linearly, square dependency on this acceleration. And this acceleration is given by Coulomb interaction, Coulomb force divided by mass. That means okay. And you see that it is square of this acceleration. Yeah. That means this is square of this. Yeah. Okay, and from this, this charge of this particle for light particle, it is electron. That means we have charge of electron. That means it will be 1. For material, we have this linear, and if it will be square of acceleration, it will be square of this z. That means dependency on this atomic number is square. That means if you have a heavy material with high z, it will be very intensive production of this Bremsstrahlung radiation. And dependency on the mass, it is here, it is 1 divided by m, and it is square of acceleration. That means will be dependency, inverse dependency on square of mass. And from this, it's possible to see why it is important, this Bremsstrahlung radiation, only for a light particle and not for heavy particle. Okay, that means it's if you will look on proton and electron, here proton, this will be this dependency, and here is electron, and mass of electron is 0.5 MeV, and mass of proton is 938 MeV. This is approximately 2,000 times heavier is proton than electron. And if you have 2,000 in square, it is 4 million. That means it is 10 to the minus 6 times smaller intensity of Bremsstrahlung radiation for proton than for electron. That means it is possible completely neglect this. The same ratio for muon in electron, because muon has 200 times higher mass than electron. It is 10 times lighter than proton. In this case, you will obtain this ratio here. That means it is 2 orders times smaller Bremsstrahlung radiation for proton than for muon. But it is clear that also for muon we have only very small probability of Bremsstrahlung radiation, and this radiation losses are negligible against this situation for heavier particles. Because these radiations are increasing with energy of this particle, and if this particle has velocity nearer and nearer to velocity of the light, this Bremsstrahlung radiation will start to increase. For muon, for very high ultra-relativistic energies, we have starts to be influence of this Bremsstrahlung radiation. Okay, that's this energy losses of electron and positron. This charge of particle is charge of electron, and this description is equivalent to pair production of the description. It is from this point of view because you know, pair production is that you have a field around atomic nuclei, and in this field you have quantum production of a pair of proton and electron. And here you have electron which is running, and you have quantum production of photon. Okay, that means it is possible to these radiation losses to describe in similar way as was for this pair production. If you remember again, here it is possible to use this basic constant, which is this radius of electron and classical radius of electron, and this constant of electromagnetic interaction. And again, that it is depending the situation of description of this production of Bremsstrahlung radiation. It is depending if you have low energies and high energies. Because for low energies, it is necessary to have strong field. And this strong field is only near to nucleus, because in outside part of nucleus, outside part of atom, you have electrons, and these electrons work as a shield of this charge of nucleus. That means this field is weak. If you have high energy, this weak field is enough to produce this Bremsstrahlung radiation. And because this part of volume is depending on third order of radius, it is this volume outside this central part of atom are much larger than this part of volume which is near to nucleus with strong field. That means if it is possible to produce electrons in weak field, it is much higher probability that it will be produced in this outer part of atom. And in central part, we have not screened this charge of nucleus. We have and this calculation is possible to do without screening for a high energy in which most part of production of Bremsstrahlung radiation is in outer part of atom. Here it is complete screening, and it is possible to use calculation with complete screening. And the results are a little different. Without screening, lower energy, and this energy are between rest energy of electron up to this. And okay, you will obtain this function as dependency on energy here. And if you remember, or if you will look on our lecture about gamma interaction and pair production, you will see that it is very similar to this, which is used for this function, which is used for pair production. For complete screening, it is possible to see that there is no dependency on energy, and it will be saturation. That means for high energy, you will obtain saturation and constant production of this Bremsstrahlung radiation. Yeah. That means for case without screening, yeah, this dependency on energy is only very weak. It is logarithmical. Here, this zeta is ratio between energy and rest energy. That means it is energy in the unit of rest energy of electron. And in the case of complete screening, it is no dependency on electron. These radiation losses are proportional, linearly proportional to energy. Yeah. In this case, okay, it's possible to calculate. Here, it's this dependency on this energy and on radiation length, which is possible to calculate from, okay, here you use this linear dependency on energy, and okay, this is this constant, and this constant is here named as radiation length. And this is from this reason, because okay, if you will use this, you will obtain that this dependency of energy losses on this path will be exponential. What is also important, okay, it is linearly increasing with energy. These ionization losses are increasing much, much slower. That means it will be some energy in which these energy losses, which are given by ionization, starts to be negligible against these radiation losses. That means for critical energy, these radiation losses are same as ionization losses. For higher energy, radiation losses dominates, and for lower energy, ionization losses dominate. For electron and positron, this critical energy is higher than rest energy of electron, and for energy, for velocity of this particle, which is near to velocity of the light. Yeah. Again, it's you know how looks like radiation losses. This is from this. You know how looks like this ionization losses. It is possible to use from beta block formula, and okay, it's possible to calculate this ratio between this radiation and ionization losses. And okay, from this it's possible to obtain which will be energy for critical energy. That means for this energy for which starts to dominate this radiation losses for increasing energy. For air is, for example, about 80 MeV. For aluminium is 40 MeV, and for lead is about 7 MeV. Okay, this total energy losses are given by a sum of ionization losses and radiation losses. And okay, here this minus is from this reason, because it is decreasing energy. Yeah. And okay, as I said, for very high energy, it is these ionization losses are negligible. For very low energies, these radiation losses are negligible. Here we have different ranges, and also it is shown, and it is possible to see how is differences between this heavy particle, charged particle interaction and light particle interaction. And it is given by this. This ionization losses for heavy particle are very small for high energies, because you have not radiation losses, you have only ionization losses, and they are small for very high velocities. Yeah, you know, it's very quick decreasing inverse square of velocity with increasing of velocity. Okay, that means, but if this velocity will start to be small, it will be very quick increase of this ionization losses, and that means that this heavy particle will stop exactly in the one point, and on the end of this range they will deposit dominate part of its energy. That means you will obtain deposition of this energy in this range distance. Yeah? And this curve is named as a Bragg curve, and it is very important and very nice, for example, for medical treatment of cancer. Yeah? Because if you will use a beam of protons for treatment of cancer, and you have, for example, tumor inside head, inside brain, where it's not possible to use knife, yeah, it is possible to put to accelerate proton on energy for which this range is exactly this distance, which is necessary for this beam to track to this tumor, and in this case all energy or dominant part of energy will be given to this tumor and destroy this cancer cells. And as I said, and as we discussed, during this scattering of heavy particle of protons, the change of track is very small, and also it will be no absorption or no change, a very big change of angle of this protons, and that means that this number of protons in the beam will be not changed up to this range of this particle. This is different situation for electrons, because you have also radiation losses. That means will be high loss of energy and with very high energy. That means, and also because it is possible to have scattering to very large angles, it will be also loss of electrons during whole track, and this is not exactly defined the range of electrons in material. That means the light particles have different situation. Yeah. Okay. Here I said you that for example, for muon, we will obtain this radiation losses, and here is this losses of energy for different particles, and here this is ionization. Okay, this is ionization losses. This is radiation losses, and here is this is total. That means for muons, this critical energy, that means for which energy this radiation losses starts to dominate, are for the energies which is hundreds GeV and near to TeV. That means there are energies which are possible only, for example, for LHC accelerator. That means for the best, for the largest accelerator in the universe or on the Earth. Okay. Okay, that I say you also that for this high energy electrons, we will obtain this Bremsstrahlung radiation and this gamma, which are produced by this very high energy electron, will be energy of this photon very high also. And after that, okay, this is high probability and dominant type of interaction is pair production, and you will obtain electron and positron. That means if they have high energy, it will be Bremsstrahlung radiation, and on the end you have electromagnetic shower with many electrons, positrons, and gammas. This angular and energy distribution of this Bremsstrahlung photons are given also by energy of this electron. This angle of in which is gamma emitted, it is given, it is inversely dependent on the energy of this electron or positron. Yeah? This is ratio between rest energy of the electron and total energy of this electron. Yeah? That and if you know from relativity, this ratio is exactly this gamma factor, this 1 divided by square root of 1 minus beta square. And if you will look that this angle is decreasing with energy very quickly. Yeah? And if energy is infinite or it is very, very high, this angle will be zero, and these photons are emitted exactly in the direction of movement of this electron. And also, this is the same for pair production. Also, if you have very high energy of gamma, these electrons and positrons are emitted exactly to direction of movement. That means for very high energy, this first part of this electromagnetic shower is this radius is very small, but for higher but for lower energy starts to be wider and wider. Okay, that means photons are, photons and also electrons are emitted to narrow cone, okay, energy distribution is that this maximal possible emitted energy is kinetic energy of electron, but okay, that this is with very small probability. There are also possible to have synchrotron radiation. In this case, it is again situation that we have some acceleration which is produced by magnetic field in which this charged particle is moving. That means if charged particle is moving in magnetic field, you have acceleration, and okay, you have emission of this electromagnetic radiation, And in this case, because this magnetic field is this intensity of magnetic fields and also this acceleration is much smaller than acceleration which is produced by this nucleus and interaction in the matter of this Bremsstrahlung radiation. This synchrotron radiation has smaller energies, and it is mostly nearer to Röntgen's X-ray radiation. This synchrotron radiation is not connected with material, but it is connected to magnetic field. This magnetic field is acting by this Lorentz force. If you remember, this is this intensity of magnetic field. This is vector multiplying by velocity, and it is here, it is charge. These energy losses are given by acceleration, the same as for this Bremsstrahlung radiation, and this acceleration which is given by this Lorentz force, but it is given also by this classical centripetal acceleration. So this is depending on v square and this radius of movement. If you put here, okay, this is acceleration square, you will obtain this energy losses for classical case, non-relativistic case. If you have a relativistic centripetal acceleration, you will obtain this for this. And again, on the end, you will obtain this V in 4, but here will be this gamma in 4. These energy losses are given by this gamma 4 and beta 4. Okay, that it is possible, and it is in this case it is very quickly increasing with velocity of this particle. This is, for example, problem for acceleration of this light particle on circular accelerator. Because you have if you have small radius and very high velocity, near to velocity of the light, you will have a very, very high intensity of this synchrotron radiation, and you have very high losses of energy. That means you have some limit of possible acceleration of these electrons and positrons on these circular accelerators. We have we discussed possible radiation, again electromagnetic radiation, which is produced if this charged particle is moving with velocity which is higher than velocity of the light in this material. This velocity, this ratio between velocity of the light in this material and in the vacuum are possible to describe by index of refraction. That if you remember, index of refraction is higher than 1. That means it should be ratio between velocity of the light in the vacuum and velocity of the light in this material. And how is with this emission of Cherenkov radiation? Okay, have a look here. If you have particle which is moving, this particle which is moving with velocity of the which is higher than velocity of the light in this material. Okay, here you have this particle, and if will be some signal which is moving with velocity of the light in this material, will be after time which is given here, t, will be here on this red circle, which was irradiate here. If will be from here, it will be here. And if will be produced here, will be here, and here will be here. And okay, you have interference of these signals or of these waves, and you will obtain wave plane which is moving in this direction and with this angle against movement of this particle. Yeah? That means, okay, and have a look here. It is perpendicular to this. That means here is 90-degree angle. Okay, here and ratio between this and this, it is cosine of this angle. Yeah, it's possible to obtain cosine of this angle. This is this divided by this. T and T is here, okay, and on the end we will obtain here is V, here is C, that means it is this beta, and we will obtain that cosine of this angle is given by this index of refraction and velocity of the light in this material, which is given by in the units of velocity of the light. Yeah. Okay, what are results of this equation? It is some threshold velocity, which is given by this refraction index, and for velocity higher than this, we will obtain emission of Cherenkov radiation, and for this velocity we will have emission of this Cherenkov radiation in the direction of movement of this particle. Yeah. Okay, for ultra-relativistic particle with velocity which is exactly velocity of the light in the vacuum, you will obtain maximal angle which will be given as inverse of this index of refraction. For some example, for water we have index of refraction 1.33. From this, it's possible to calculate minimal necessary velocity as 0.75% of velocity of the light. And if you will use these relativistic equations, it's possible to calculate kinetic energy of electron. Yeah, that's okay. It's maybe it will be fine homework for you. And okay, that this maximal cosine of maximal of this angle will be 0.75, and if you will check what is result, this angle is about 41.5 degree. Okay, last part is last possible interaction, which is interaction of this charged particle which are running through different materials, and if charged particle throws some boundary which are from different materials which have different index of refraction, in this case also we will have emission of electromagnetic radiation. It was discovered by Ginzburg and Frank in 1946. In this case, it is some creation of dipole in boundary zone, and dipole electromagnetic field are changing in time, and that means it is changing, and it is emission of electromagnetic radiation. Okay, it is also emission of energy during transition from material to vacuum. Yeah, but probability of such radiation, it's very, very small. That means it is necessary, if you want to use, for example, this phenomena for detection of this particle, it is necessary to have many of these boundaries. That means it's necessary to have many, many layers of different materials. This energy is given by this formula. This gamma This is this Lorentz factor. That means this from this special relativity. It is done by frequency, which is characteristic plasma frequency in this case. And here it is about 14 electron volts for lithium, and therefore different materials. But you see that it is very small. Yeah. This alpha, this is this constant of electromagnetic interaction. Yeah, this hyperfine constant. This 1 divided by 137. And it is possible to see if here this is only 14 electron volts. Yeah. Here is 1 divided by 137. Yeah, this is 1/3. It will be very, very small number. Yeah, and energy of this emitted. This is energy which is emitted by this transition. But energy of emitted photons, it is from 10 to 30 keV. Here is electron volts. Here is keV. Yeah, that means that probability of emission should be very, very small because emitted photons have very high energy. Yeah? And it's possible to calculate number of this photon. This is this energy, which will be very small, and divided by energy of this emitted photon. Yeah, but this energy is increasing very quickly with gamma factor. That means with velocity. And if this velocity will be very near to velocity of the light, will be this probability higher and higher. But in any case, this number of photons is very, very, very small. That means it's necessary to have many hundreds of these layers. Fine, as I said, that it is necessary to have many layers of this material because this probability of in emission of photon is very, very small. Also, in this case, this emission of this transition radiation photons, which are, as I said, it is in the range of from 10 to 30 keV. This is in approximately in the range of X-rays. Yeah, that means it is Röntgens, not as Cherenkov radiation. This Cherenkov radiation is in the visible range of spectra of electromagnetic radiation. This direction of light will be for higher and higher velocities, nearer and nearer to velocity of the light, smaller and smaller angles. That means it will be in the direction of the movement of this particle. These radiators for transition radiation, it should be materials with small z. And because this is from this reason, because reabsorption increases with because it is small, it is low energy. Yeah, this is low energy photons from point of view of gamma, yeah, or X-rays. And if you remember, in this energy range, probability or cross-section of photo effect is in 5 order. Yeah, that means it is very if you have heavy atom, it will be very high probability of photo effect. That means it will be very high probability of absorption of this X-ray photons which are irradiated by this transition radiation. It's necessary to work on good combination of radiators and X-ray detectors, which are used for detection of this transition radiation. And for example, such transition radiation detectors are used also for this LHC experiments.